Okay, so boron trifluoride asks us first of all for an equation. So boron, it tells us, is just B. Fluorine, on the other hand, you have to know is F2. And that should be easy. It's a group 7 element, so it does the same thing that chlorine, bromine and iodine do, which you've learnt are diatomic molecules. So fluorine is F2, and they react together to give you BF3, and clearly there's a little bit of balancing needed there. The easy way to do it is just to put 1.5 in front of the fluorine, because that will give us the 3 fluorine atoms to balance it up. If you prefer, you can have 2 borons and 3 F2s to give you 2 BF3, and that would be fine as well. Okay, so now we get on to the shape of the BF3 molecule. Generally speaking, when you ask to figure out the shape of a molecule, what you need to have is a dot and cross diagram, at least in your head, but to be on the safe side, down on paper. Now, you don't have to write it in as part of your answer, so you can do it in rough, but it's crucially important that you have thought about what electrons there are, what electron pairs there are in the outer shell of the middle atom, which in this case is the boron, because remember, it's those electron pairs that determine the shape. So let's do that dot and cross diagram, even though, as I say, you don't have to do this as part of the answer, it's just that the thinking has to be there. So boron has 3 fluorines around it, 1, 2, 3, like that, and because it's a group 3 element, it has only 3 electrons in its outer shell. So if it uses 1 to bond to each fluorine, so we have a shared pair there, and another one there, and another one there, then that's it as far as the boron's concerned. It's used its outer shell electrons up, no lone pairs. The fluorines do have, in fact, 3 lone pairs each, and if you were asked to do the dot and cross diagram formally, you'd have to stick all those in, so you'd have shared pairs like this and this and this. But they actually don't matter for the shape, so if you're just doing this in rough, then obviously you don't need to waste time doing that. The crucial thing is what's going on, remember, always around the central atom. So now we'll come to what you do actually have to write down in your answer. And generally, whenever you have to justify a shape, if you make some kind of statement along the lines of what we're going to do now, that's a good way to encapsulate the important ideas. So what we can say is that boron has, well, what does it have? It has 3 bonded pairs, and it has no lone pairs. Okay, so that's just looking at what you've got in the outer shell, and you've got to explain what the point about that is. So those electron pairs are repelling each other, because that, remember, is what determines the shape. Electron pair repulsion, repelling each other in its outer shell. Okay, so that's a good template to use when you're explaining shapes, is to identify what the middle atom is that you're focusing on, list what bonded pairs, what lone pairs, and where appropriate also what double bonds. There aren't any here, so you didn't have to mention them, but if there are double bonds, remember they repel just as if they were a single bonded pair. So list those as well if necessary, and then explain that those repel one another. That's what determines the shape, and that you've just been thinking about the outer shell electron pairs, because those are the ones that matter for this. Okay, so that's your general statement, and then we've got to say, okay, so what is the shape you get as a result of that? And the shape you should have learnt, if you've got 3 bonded pairs repelling each other, is called trigonal planar. Okay, so you've got to learn these shape names, and in this particular question, the little pencil picture there tells you not only did you have to know it, you had to spell it right to get the mark. You also had to state the bond angle, which again you need to learn, and in this case, in fact, if you weren't entirely sure, it's easy if you just sketch it down. You didn't have to do this, but you could do. The fact that it's planar tells you that all of those 3 fluorines, and indeed the boron, are in the same plane. So they're equally spaced around that central boron, and so the 3 bond angles will add up to a circle, will add up to 360 degrees, and so that one, or any one of them, is just a third of that, so it's 120 degrees. Okay, so that's all you need to get your 4 marks on that question. So now we are into looking at nitrogen trifluoride. This question is a tricky one in a way, in the sense only that it's just 2 marks. It could have been a much bigger question, because it could have asked us to go into details about why this molecule has the shape it does, which is different from BF3, and because all of that is crucial for its having a dipole. But the fact that it's only 2 marks means you don't have space to do all of that. So what we'll do is initially just focus on the key points you have to make to get the 2 marks, but then we'll also just remind ourselves about why it's different from BF3. So if you're asked to explain why a molecule is polar, or indeed why it isn't polar, there are really 2 important issues. The first is that you have to consider whether the individual bonds in the molecule are polar, because clearly if none of them are, then the molecule as a whole can't be. So the first thing is that the bonds have to be polar, and bonds are polar when you have differences in electronegativity. So the first thing you have to establish in this question is what's the relative electronegativity of nitrogen and fluorine. And it wasn't enough just to say that, oh well, they're different. You had to get the trend the right way round. So remember that as you go across a period, and nitrogen and fluorine are both there in period 2, but fluorine's further over to the right, as you go across the period, electronegativity increases in the same way that ionization energy increases, because in both cases it's about how strongly electrons are attracted to the nucleus. So fluorine is more electronegative than nitrogen because it has a bigger nuclear charge, essentially pulling on the same outer shell. And the consequence of that is that when it shares electrons with nitrogen, the fluorine does a better job of pulling them towards itself, so it gets more than its fair share of those negatively charged electrons, so it becomes delta negative, slightly negatively charged. Okay, so to get the first mark, you had to explain that the NF bonds are polar because fluorine is more electronegative than nitrogen. And so the consequence of that, and you can just do this most easily just by marking it on the bond, is that the nitrogen will be delta positive, meaning it's got less than its fair share of the shared electrons, and the fluorine is delta negative, meaning that it's got more than its fair share. Okay, so that's the first marking point. Now, that's not enough to give you a molecule which as a whole is polar, because quite often the symmetry of the molecule causes the dipoles associated with those individual bonds to cancel out. So the fact that NF3 is polar overall tells you that that doesn't happen. And in fact all you needed to say to get the second mark was that the NF3 molecule does not have enough symmetry for the individual dipoles to cancel out. And that must be true. So even if you're not sure what the shape is, you can see that that has to be true in order for their statement, which is that it has a permanent dipole, in order for that to be true. So that's your second marking point. Okay, that would be enough to complete the answer to the question. But let's just see why that's the case. Because we've already seen that with BF3, you get this trigonal planar shape, like that. And in fact, in that case, again you have polar bonds, with the boron being delta positive, but the symmetry is such that those individual dipoles do cancel out, and that molecule doesn't have a dipole moment. So what's different about NF3 is that nitrogen's in group 5, not group 3, So when we put nitrogen in the middle there, you have 5 electrons in the outer shell, only 3 of which are involved in making the 3 shared pairs, and the other 2 form a lone pair. And so now you have repulsion between 3 bonded pairs and 1 lone pair, and the shape that gives you is different, and specifically it's this pyramidal shape. Okay, so you could have stated all of this, that the shape of NF3 is pyramidal, and that shape is less symmetrical, so the individual dipoles don't cancel out. Okay, and you can see why that is, that the nitrogen's up here and all of the 3 fluorines are down there, so you have a positive end of the molecule and a negative end of the molecule. So that's just fleshing out a bit the detail behind these ideas, but these were the crucial points you had to get the marks. And finally, we're asked to describe and explain the trend in atomic radii as you go across period 2. So remember that atomic radii are one of these things which depend essentially on the strength of attraction between electrons and nuclei. So there's a whole raft of these things. Ionization energies, electronegativities, strength of oxidizing agents when you're comparing the halogens in group 7, they all come down to this idea of comparing ability to attract electrons in the outer shell to the nucleus. And atomic radius is about that as well, because simply the stronger the attractive force pulling the electrons in towards the nucleus, then the smaller the atom will become. So, what do we have to do? Well, first of all, we have to state what the trend is. And yes, you could figure it out using those ideas we've been alluding to, but that's dangerous. You've really got to learn it and make sure you get it the right way around. So the trend is that as you go across the period from left to right, the radii decrease. Okay, so first of all, make sure you've got that written down then, that the atomic radius decreases across the period. And then the question is, well, why does it do that? So to explain that fully, you need to be essentially using this checklist, the same as you would with ionization energy. So let's remind you of the general things you need to be talking about, and then see how that applies to this particular question. So remember, you need to talk about the nuclear charge, which means the number of protons, but you should try and use that phrase to emphasize that it's the fact that it's a positive charge attracting the electrons towards it, and the size of that positive charge affects the strength of attraction. Then you need to talk about what shells the atom has. When you're comparing things, if you change the number of shells, then you have big consequences of that. Both of those things relate to the distance of the outer electrons to the nucleus. And obviously that's the crucial thing when we're talking about atomic radius, because atomic radius is essentially the distance of the outer electrons from the nucleus. So if we were talking about ionization energies, you just talk about that as one of the factors. But here, obviously, in a sense, it is the outcome of all of the other factors is what's the distance to the outermost electrons. But the other thing that the shells influence is how much shielding there is. Remember, that's repulsion from electrons in inner shells. So the more shells you've got, the more shielding you've got. And all of those things together affect the attraction to the nucleus. And as we said, that's crucial to limiting the radius of the atom. So how do we talk about all of those things in this particular case? Well, as you go across the period, the nuclear charge clearly increases because you're adding one more proton to the nucleus as you go from each element to the next across the period. The shells, well, each of the elements in the period has the same outer shell because you're just filling up that shell, but you're not adding on any new shells. So the same outer shell. Therefore, the shielding doesn't change very much. Okay, the shielding only changes significantly when you add on a whole extra shell. So if you put those ideas together, the attraction to the nucleus increases as you go across the period, and therefore the distance to the outermost electron decreases, which amounts to saying that the atomic radius decreases. Okay, so you use the checklist, you just kind of structure your argument in a slightly different way than you would when you were talking about ionization energies. So increasing nuclear charge across the period, outermost electrons in the same shell, so similar shielding, therefore overall increasing attraction to the nucleus. Don't just say attraction, it's got to be attraction to the nucleus. That increases as you go across the period, and therefore the distance to the outermost electrons will decrease, which is equivalent to saying the atomic radius decreases. And that finally is the end.